Alright folks, welcome back to the channel here. Today I'd like to talk about something called Nyquist Zones. You can Google that for more mathematical thing, but today I'd like to just give a quick talk about how we can use Nyquist Zones so that we don't need mixers and local oscillators. So let's go through a classic example here. We've got a nice 1 megahertz sine wave coming in here. And then we're going to have it go into a nice little low pass filter with a cutoff frequency of 50 megahertz there. Then we'll feed that into a nice little A to D, standing for analog to digital converter. And it's running at a clock of 100 megahertz. And then we're going to have some sampled signal here. We'll call that X of N. And I think it's pretty clear that X of N here is going to be a discrete 1 megahertz sine wave. So that's pretty simple. And this is your classic setup. But now I'm going to do something that's going to blow your mind. Well, now let's say we're going to get rid of that low pass filter. And let's say we have coming into this A to D 101 megahertz sine wave. Now remember, the A to D, the analog digital converter, is still running at 100 megahertz clock. Our question today is, well, what's X of N going to be? Well, X of N is going to be 1 megahertz. That's what we call aliasing. The 101 analog signal is aliasing down to 1 megahertz. Now classically we're told that's bad. Never, never, never do that. But what they don't say is if the bandwidth of the 101 signal that we're trying to sample is smaller than the bandwidth of the clock, you can kind of get away with it. And what that means is that we don't need to put mixers here. We can just have the 101 signal come in, get digitized, and we know that if we have a 100 megahertz clock, a signal at 101 will alias down to 1 megahertz in the digital domain. So that's a neat little trick that we can do, and again it's called exploiting or using what's called Nyquist zones. For those of you that think this is silly willy and not used, well, you're completely wrong. This is exactly what's used in your little smartphones. Haven't you ever wondered why there's no local oscillators in there? That's because the people that make the smartphone are some clever little people. And they exploit this idea right here. They'll have the A to D chip running at 100 megahertz or maybe a gigahertz, 2 gigahertz, whatever. And they'll just put some filters up here and they'll know where it will fold down based on the Nyquist theory. So this is one way how we can sample high frequency signals with a lower clock A to D. Ain't that something? Here's the same thing again here. Let's say instead of a 101 megahertz sine wave, we now have a 201 megahertz sine wave. Again, the A to D is still running at a 100 megahertz clock. And our question today is, what will X of N be? X of N will still sample down to 1 megahertz. So you can start seeing there's many Nyquist zones that we can exploit. So that's a pretty nifty idea. Alright, so here you go. Here is what's called our Nyquist zone. So we got the first Nyquist zone here. That's 0 to half the clock. This is your traditional zone. And then we got this zone up here at the first sample rate. So this will be a bandwidth of, in our case, 100. So it'll be a bandwidth of 100 megahertz. And then we got 2FS. That's going to be 200 megahertz. That's another zone we could sample. Or we could do 3FS. That would be 300 megahertz. Now, realistically, you generally don't go past 3FS. Mathematically says it goes on indefinitely. That's not the real world. So you can probably get away with maybe FS, 2FS, and if really pushing it, 3FS. The problem will be maybe the loss will be a little bit more, but you can still make up for that with some LNA at the front. But the nice idea is that we can use this concept of Nyquist zones so that we don't need to make mixers and local oscillators to shift the frequency down. We can do that shifting by taking advantage of aliasing. Alright? And here would be the design. Let's say we're interested in radio signals from 50 megahertz to 150 megahertz. And we want to use an A to D that runs at 100 megahertz clock. This would be the idea. And the idea is that the frequencies would alias once they're in digital, but because we have that bandpass filter in front of the A to D, we know the signals, only the signals the A to D can see are signals between 50 and 150 megahertz. And the reason why that bandpass filter becomes very critical is, like back in my example, if we had a signal that was at, say, 1 megahertz, we want to make sure that that signal cannot get into the A to D. Because when we see 1 megahertz in the A to D space, we think that input signal was 101 megahertz. So when you do this idea of Nyquist zones, the critical component now becomes the bandpass filter. And that bandpass filter has to make sure that it does not allow signals outside of the Nyquist zone that you're trying to digitize. So that's one trade-off why this may or may not be done. But again, it's becoming very common now as our A to Ds and DACs are getting at clocks of 1 gig, 2 gig. We can start using this idea and save us some mixers and local oscillators in the hardware. So I hope you learned something today about Nyquist zones. And for those of you that would like to see the detailed math and gory this, gory that, Google away and you'll get all the details. But this is a practical, application-based idea of how you could use Nyquist zones. Now what I have shown is only for A to D sampling, but you can do the same thing on the DAC side as well. And again, the idea there is you wouldn't need mixers and oscillators to mix the signal up. You can just have it come out at a Nyquist zone out of the DAC and you're already there. Ain't that something? And I'll leave you with one little financial tip. One of the companies that's making these very specific bandpass filters, particularly in smartphones, is a company called Resonant, and its stock is RESN. It just jumped from $150 to $4. Thankfully, I was in the stock. But I would still encourage you to buy the stock, because that is the future of our 5G phones. And these will be used heavily in all of your new smartphones that you might be actually watching this video on right now. Well, until next time, this is Moonshine Radio. Have a good day.